It's the most powerful technology of our time. But how does artificial intelligence actually work? We're pulling back the curtain. This is AI Deconstructed.
In our previous episodes, we've explored the world of supervised learning, a domain where our algorithms learn from data that has been meticulously labeled by human experts. We had a teacher, a guide, providing the correct answers, telling the machine this image is a cat, this email is spam, this house sold for this exact price. We were, in essence, solving for known unknowns. We knew the question we wanted to answer, and we had the examples to learn from. But what happens when there are no labels, no teacher, no answer key? Imagine you are an archaeologist who has just unearthed a library of scrolls from a lost civilization. There are no dictionaries, no Rosetta Stone, no labels of any kind. How would you begin to make sense of it all? You might start by grouping scrolls with similar scripts, or sorting them by the material they're made of, or clustering them by recurring symbols. Without a teacher to tell you what's correct, you would be forced to find the patterns inherent in the chaos. This, in essence, is the challenge and the power of unsupervised learning. Today, we journey into the realm of unknown unknowns. It's about giving a machine a vast, unlabeled dataset and asking it a simple but profound question. What's interesting in here? Find the structure. We're going under the hood of this exploratory paradigm. We'll define its core principles, dissect its two primary tasks, clustering and dimensionality reduction, and then get our hands dirty with two legendary algorithms, k-means and principal component analysis. We'll also confront a formidable challenge known as the curse of dimensionality, and see how these tools help us overcome it. Finally, we'll see how this learning without a teacher is reshaping entire industries, from marketing to medicine. Let's begin. To truly grasp unsupervised learning, we must first solidify its contrast with its supervised counterpart. The single biggest difference, the one from which all other distinctions flow, is the type of data used for training. As we've established, supervised learning algorithms train on labeled data. This means for every input data point, we have a corresponding correct output or label. An algorithm is shown thousands of pictures of animals, the inputs, along with their correct species names, the labels. Its goal is to learn the relationship, the mapping function, between the input and the output, so it can later predict the labels for new unseen animal pictures. The goal is explicitly defined and measurable. Minimize the error between the model's predictions and the true labels. These models are built for prediction tasks, which generally fall into two categories: classification like spam detection and regression, like forecasting the weather or predicting price changes. Unsupervised learning, on the other hand, operates in a world of unlabeled data. The algorithm is given only the inputs, the raw data, and must work independently to learn the data's inherent structure. There is no correct answer provided. We simply provide the dataset and let the algorithm identify any naturally occurring patterns, similarities, or differences. The goal here is not prediction in the same sense, but rather discovery and data exploration. It's about finding hidden structures you didn't know existed. This fundamental difference in data and goals leads to entirely different applications. While supervised learning excels at predicting known outcomes, unsupervised learning is the engine for exploratory analysis, used for tasks like clustering, for example, customer segmentation, association, for example, market basket analysis, and dimensionality reduction, for example, big data visualization. It's also worth noting that this is not a strict binary. A third category, semi-supervised learning, exists as a bridge between the two. This approach uses a small amount of labeled data to help guide the learning process on a much larger pool of unlabeled data, combining the best of both worlds when labeling is expensive or time-consuming. This distinction between supervised and unsupervised learning is not merely a technical detail. It reflects two fundamentally different modes of scientific inquiry. Supervised learning is analogous to hypothesis testing. A scientist starts with a specific question: can we predict housing prices from these features? And a known target variable, the actual prices. The labeled data represents a controlled experiment designed to confirm or deny this hypothesis. Unsupervised learning, conversely, is the embodiment of exploratory discovery. It's akin to an astronomer pointing a powerful new telescope at a patch of sky for the first time, or a biologist sequencing a novel genome. There is no specific hypothesis being tested. The goal is to see what's there, to map the terrain, to discover new galaxies, new genes, new structures that you didn't even know to ask about. Therefore, the choice between these paradigms isn't just about whether you have labeled data. It's about the fundamental purpose of your investigation. Are you trying to confirm and predict based on established knowledge, or are you venturing into the unknown to discover something entirely new? This reframes unsupervised learning not as a lesser form of machine learning that simply lacks labels, but as a powerful, indispensable engine of primary discovery. Now that we understand the philosophy, let's look at the tools. Unsupervised learning is a broad field, but its tasks can largely be distilled into two major categories: finding groups and simplifying complexity. At its heart, clustering is a data mining technique for grouping unlabeled data based on similarity or, conversely, differences. The fundamental goal is to create clusters where the data points within a single group are very similar to one another, while being very different from the data points in other groups. Think back to our archaeologist with the unlabeled scrolls. Grouping them by the type of script used is a clustering task, or consider a biologist discovering hundreds of new insect species. Before they can be formally named and classified, the biologist might first group them based on shared physical traits like wing shape, color, and number of legs. This initial grouping is clustering. A more everyday analogy is sorting a large box of mixed candies. You might not know the brand name of each candy, but you can easily group them by flavor. All the chocolates in one pile, all the sours in another, and all the fruity ones in a third. You have just performed a clustering task. There are several families of clustering algorithms, each with a different approach to forming these groups. First, there's partitioning clustering. This is often called hard or exclusive clustering. In this approach, the data is divided into a predefined number of non-overlapping clusters. Each data point belongs to exactly one cluster. The most famous and widely used partitioning algorithm, which we will dissect shortly, is k-means. Then there's overlapping clustering, also known as soft clustering. This approach allows a single data point to belong to two or more clusters with varying degrees of membership. This is useful in cases where categories are not mutually exclusive, like classifying movies that could be both a comedy and a romance. Finally, there's hierarchical clustering. This method doesn't produce a single flat set of clusters, but rather a tree-like hierarchy of clusters called a dendrogram. It works in one of two ways. One is agglomerative, a bottom-up approach where each data point starts in its own cluster, and pairs of clusters are merged as one moves up the hierarchy. The other is divisive, a top-down approach where all data points start in one giant cluster, which is then split recursively as one moves down the hierarchy. The second major task in the unsupervised toolkit is dimensionality reduction. First, Let's define dimensions. In machine learning, a dimension is simply a feature or a variable in your dataset. If you have a dataset of customers, you might have features like age, income, number of website visits, time spent on site, and total amount spent. This would be a 5-dimensional dataset. Now, 5 dimensions is manageable. But what about a dataset of facial images where every single pixel is a dimension? A simple 100 by 100 pixel image has 10,000 dimensions. Or consider a dataset in genomics, where researchers might measure the expression levels of 20,000 different genes for each patient. Suddenly, we are dealing with datasets of tens of thousands of dimensions. Working with such high-dimensional data presents a host of problems, which we will explore in depth later under the ominous name, the curse of dimensionality. For now, it's enough to know that it makes finding patterns incredibly difficult and computationally expensive. Dimensionality reduction is the process of reducing the number of these features or variables, while trying to retain as much of the important information, the variance or structure, as possible. It's a method for simplifying data. A good analogy is writing a summary or an abstract of a long, dense book. You are reducing the number of words, the dimensions, significantly. In doing so, you will inevitably lose some of the finer details and nuances of the prose. However, a well-written summary preserves the main plot points, the key characters, and the central theme. You've reduced the complexity while retaining the essence. Dimensionality reduction aims to do the same for data, and the premier technique for this task is principal component analysis, or PCA. Let's roll up our sleeves and dive into our first algorithm. If there is one clustering algorithm you should know, it's k-means. It is the undisputed workhorse of partitioning clustering, simple, intuitive, and surprisingly powerful. The goal of k-means is straightforward: to partition a set of n data points into k, distinct, non-overlapping clusters. The k in k-means is a number we, the user, have to specify. It's a hyperparameter, a setting that we provide to the algorithm before it starts running. It represents the number of clusters we are looking for in the data. The algorithm's core objective is to find the cluster assignments that minimize a criterion known as inertia, or more formally, the within-cluster sum of squares, WCSS. Let's break that down. It sounds complex, but the intuition is simple. We want to find cluster centers such that the total sum of the squared distances from every single data point to the center of its assigned cluster is as small as possible. In other words, we want to make the clusters as compact and tightly packed as possible. This objective has a formal mathematical definition, but the intuition is what's important. It's just a formal way of saying, for each data point, find the distance to the nearest cluster center, square that distance, and then sum up all those squared distances for every point in the dataset. Our goal is to make that final sum as low as we can. To achieve this, k-means uses the concept of a centroid. A centroid is the geometric heart or center of gravity of a cluster. It is simply the arithmetic mean, the average position, of all the data points that belong to that cluster. It's important to note that the centroid itself is not usually one of the original data points. Rather, it's a new point that represents the center of a group. The k-means algorithm, often referred to as Lloyd's algorithm, is an iterative process. It doesn't find the perfect centroids in one go. Instead, it refines their positions over and over again in a kind of elegant dance until it settles on a stable solution. Let's imagine you're a teacher with 10 students in a classroom. You don't know anything about them, but you can see their height and weight. You decide you want to split them into 2 groups. So k equals 2, based on these physical characteristics. Here is how k-means would do it. First is the initialization step. The algorithm needs a starting point. It randomly selects k data points from the dataset to serve as the initial centroids. In our classroom, we would just randomly pick 2 students and declare them the temporary group leaders or initial centroids. This random start is a crucial point we'll return to, as it can influence the final outcome. Second is the assignment step. Now, the algorithm goes through every single data point, every student, and calculates its distance to each of the k centroids. The distance is typically the standard Euclidean distance, which is just the straight-line distance between 2 points. Each data point is then assigned to the cluster of the centroid it is nearest to. So each of our 10 students would look at the 2 group leaders and join the group of the leader they are more like in terms of height and weight. Geometrically, this step carves up the entire data space into k regions, where each region contains all the points closest to one particular centroid. This partitioning is known as a Voronoi diagram. Third is the update step. Once every student has been assigned to a group, the initial group leaders might not be the true centers of their new groups anymore. So we need to update them. The algorithm recalculates the position of each of the k centroids. The new position for a centroid is simply the mean or average position of all the data points that are currently assigned to its cluster. In our classroom, we would find the average height and weight of all students in Group A, and that average becomes the new leader A. We do the same for Group B. The centroids have now moved from their initial random positions to the actual centers of the groups formed in the assignment step. Fourth is convergence. Now we repeat. With the new updated centroids, some data points might now be closer to a different centroid than they were before. So we go back to the assignment step, reassigning all points to their new nearest centroid. Then we go back to the update step, recalculating the centroid positions based on the new assignments. This loop, assign, update, continues. With each iteration, the centroids shift and the cluster memberships are refined. The algorithm stops or converges when the assignments no longer change. That is, when an iteration of assigning and updating results in the centroids staying in the exact same place, we know the solution is stable and the algorithm is finished. We are left with our final k clusters and their corresponding centroids. This iterative refinement process is a form of a powerful and general statistical optimization method known as the expectation maximization (M) algorithm. This connection is more than just a piece of trivia. It places k-means within a much broader family of algorithms used across statistics and machine learning for problems involving missing or hidden data. In the context of k-means, the hidden or latent variable for each data point is its true cluster identity, which is precisely what we are trying to find. The assignment step is the expectation or STIP. Here, we use our current model, the centroid positions, to make our best guess about the hidden variables. We expect each point to belong to the cluster of its nearest centroid. The update step is the maximization or M step. Here, we take those assignments as if they were true and update our model parameters, the centroid positions, to the locations that best fit or maximize the likelihood of that data assignment. By viewing k-means through this lens, we can see it's not just an ad hoc geometric trick. It is a principled optimization procedure, grounded in rigorous statistical theory, that seeks to find the best possible explanation for the hidden structure in our data. We've walked through the elegant dance of the k-means algorithm, but we've glossed over the most pressing practical question a data scientist faces when using it. How do we know the right number of clusters? How do we choose the value of k? After all, The algorithm requires us to specify k up front, but the whole point of unsupervised learning is that we don't know the underlying structure of the data. There is no single perfect answer to this question, but one of the most common and intuitive heuristics is called the elbow method. The procedure is as follows. Run the k-means algorithm several times on the dataset, each time with a different value of k. For example, you might run it for k equals 1, k equals 2, k equals 3, all the way up to k equals 10. For each value of k, you calculate the final WCSS, the inertia or within cluster sum of squares, for the resulting clustering. You then plot the values of k on the z-axis against their corresponding WCSS values on the y-axis. What you will see is a curve that generally goes down. As you increase k, the WCSS will always decrease. This makes sense. If you have more clusters, the points within each cluster will be, on average, closer to their respective centroids. In the extreme case where k is equal to the number of data points, the WCSS would be 0, as each point would be its own cluster. However, we are looking for a natural grouping, not just minimizing WCSS. The key is to look for an elbow in the plot, a point where the rate of decrease in WCSS sharply flattens out. The idea is that adding another cluster beyond the elbow point doesn't provide much better modeling of the data. That elbow point is considered a good indicator of the optimal number of clusters, representing a good balance between the number of groups and the overall compactness of those groups. It's a heuristic, not an infallible rule, but it provides a data-driven way to approach the critical question of choosing k. Before we move on to our next algorithm, we need to address a formidable challenge that looms over much of machine learning, and particularly over unsupervised methods that rely on distance. It is a counterintuitive and deeply important concept known as the curse of dimensionality. The term was coined in the 1950s by the brilliant mathematician Richard Bellman while working on problems in dynamic programming. It describes the various problems that arise when analyzing data in high-dimensional spaces. Intuitively, we tend to think that more data is always better. More features, more information should lead to better models. The curse of dimensionality teaches us that this is dangerously naive. The core cause of the curse is the exponential growth of volume as you add dimensions. Let's use a simple analogy to build our intuition. Imagine you want to ensure you have data points that are, on average, no more than 0.1 units apart. In a single dimension, a line of length 1, you would need about 10 data points to cover it adequately. Now let's move to 2 dimensions, a 1 by 1 square. To maintain the same data density, you now need 10 times 10 or 100 points. In 3 dimensions, a 1 by 1 by 1 cube, you need 10 times 10 times 10 or 1000 points. By the time you get to a 10-dimensional hypercube, you would need 10 to the 10th power or 10 billion data points to maintain the same coverage. The volume of the space explodes so rapidly that any fixed amount of data becomes incredibly sparse. Your data points, which might have seemed close in a few dimensions, are now floating in a vast, empty void. It's like trying to find constellations in an ever-expanding universe. The stars just get farther and farther apart. This sparsity has several devastating consequences for machine learning algorithms. First, distance metrics fail. This is perhaps the most critical consequence for algorithms like k-means. In high-dimensional space, a strange geometric phenomenon occurs. The distance to a data point's nearest neighbor and the distance to its farthest neighbor become almost equal if all points are roughly equidistant from each other. The very concept of nearness or a neighborhood loses its meaning. An algorithm that relies on finding the nearest centroid is fundamentally broken if everything is equally far away. Second, overfitting. When the number of features, dimensions, starts to approach or exceed the number of observations, a model has so much flexibility that it can find spurious patterns in the random noise of the training data. It learns the training set perfectly but fails miserably when it encounters new unseen data because the patterns it learned weren't real. This is overfitting. Third, increased computational cost. More dimensions simply mean more numbers to process. The computational resources and time required to train a model can grow exponentially, making many problems intractable. This reveals a fundamental tension in machine learning between information and noise. While adding a new feature could, in theory, add valuable information, it is statistically more likely to add noise and redundancy. This leads to a phenomenon known as the Hughes phenomenon, which states that for a fixed number of training samples, the predictive power of a model will at first increase as you add dimensions, but beyond a certain point, performance will start to degrade as the noise from irrelevant features overwhelms the signal from the useful ones. So, how do we escape this curse? The solution is not just about developing more powerful computers or collecting more data, which can be impractical. The truly elegant solution lies in a profound realization about the nature of real-world data, often called the manifold hypothesis. This hypothesis suggests that even when our data is presented to us in a very high-dimensional space, like the thousands of pixels in an image, the data itself often lies on or very close to a much lower dimensional structure or manifold, embedded within that high-dimensional space. Think of the flight path of a satellite orbiting the Earth. Its position at any given time can be described by three spatial coordinates, x, y, z, making it seem like a 3D problem. However, the path itself is just a unidimensional line curving through that 3D space. The intrinsic dimensionality of the satellite's path is 1, not 3. The manifold hypothesis posits that this is true for much of the data we care about. The challenge, then, is not to try and analyze the data in the vast, empty, high-dimensional space, but to discover and work within the much simpler, lower-dimensional manifold where the data actually lives. And that brings us perfectly to our next algorithm, a tool designed for precisely this purpose. If the curse of dimensionality is the problem, principal component analysis, or PCA, is one of the most powerful solutions. It is the premier classical technique for dimensionality reduction. It is a method for taking a dataset with many variables and reducing it to a smaller set of summary indices, while retaining most of the original information. Perhaps the most intuitive way to understand PCA is through a visual analogy. Imagine you have a three-dimensional cloud of data points. Like a swarm of bees frozen in midair, it's hard to see the overall structure of the swarm from just one angle. PCA is like finding the best possible camera angle from which to view this 3D cloud. It rotates the coordinate system to find a perspective where, when you project the 3D data onto a 2D photograph, you see the most possible structure and spread in the data, losing the least amount of information in the process. It is, fundamentally, about changing your vantage point to get a better, simpler view of your data. So how does PCA find this best angle? The core idea is to transform the data by creating a new set of variables, called principal components, PCs. These new variables are not chosen arbitrarily. They have very specific and useful properties. First, They are linear combinations of the original variables. This means each principal component is a weighted sum of the original features. For example, in a financial dataset, a PC might be something like 0.7 times tech stock returns, plus 0.5 times industrial stock returns, minus 0.2 times bond returns. Second, they are uncorrelated with each other. This is a critical property. Often our original features are highly correlated, e.g., a person's height and weight. This correlation represents redundant information. The principal components are constructed in such a way that they are all statistically independent, meaning each one provides unique information. Third, they are ordered by the amount of variance they explain. This is the secret sauce of PCA. The first principal component is constructed to capture the largest possible amount of variance in the dataset. The second captures the next largest amount of variance, and so on. The process works intuitively, like this. First, PCA scans the entire dataset to find the single direction through the data cloud along which the data is most spread out. This direction of maximum variance becomes the first principal component, PC1. It represents the single most important dimension in the data. Next, it looks for another direction. This new direction must be orthogonal or perpendicular to PC1. Subject to that constraint, it finds the direction that captures the next highest amount of remaining variance. This becomes the second principal component, PC2. This process continues, with each subsequent principal component being orthogonal to all the ones before it and capturing the maximum possible amount of the remaining variance, until we have as many PCs as we had original dimensions. The result is a brand new coordinate system for our data, defined not by the original features, but by the principal components. The magic of PCA is that most of the variance in the original dataset is often concentrated in just the first few principal components. By choosing to keep only the first few PCs, for example, PC1 and PC2, and discarding the rest, we can dramatically reduce the dimensionality of our data, while retaining the majority of its original information or signal. It is, in effect, a form of intelligent, lossy data compression. We've thrown away the dimensions that contain the least information, the noise, and kept the ones that contain the most, the signal. We have found the manifold. Theory is essential, but the true test of any machine learning paradigm is its impact on the real world. Unsupervised learning is not an academic curiosity. It is a driving force behind countless applications that shape our modern world. Let's look at some concrete examples. The ability of k-means to find natural groupings in data has made it an indispensable tool in many industries. The quintessential application is customer segmentation. Businesses collect vast amounts of data on customer behavior, what they buy, when they buy, how they browse a website. K-means can be used to cluster customers into distinct segments, for example, high-spending loyalists, bargain-hunting newcomers, or infrequent visitors. By understanding these groups, a company can move beyond one-size-fits-all marketing and create tailored strategies, personalized offers, and optimized product recommendations for each segment. Another is anomaly and fraud detection. In a data set of financial transactions or network traffic, most of the data will follow predictable patterns. Fraudulent transactions or malicious network attacks, however, are often outliers. K-means can be used to cluster the normal behavior. Any data point that does not fit well into any of the normal clusters can then be flagged as a potential anomaly for further investigation. This is used by banks to detect unusual credit card activity and by IT departments to identify security threats. Then there's document clustering. Imagine you have 1,000,000 news articles with no categories. K-means can be used to automatically group these documents based on their content. By analyzing word frequencies, it can discover clusters that correspond to topics like sports, politics, technology, and finance, all without being told what those topics are beforehand. This is invaluable for organizing and searching vast libraries of text, from legal documents to scientific papers. And in bioinformatics, the impact is profound. Researchers can analyze gene expression data from hundreds of cancer patients. Each patient's data is a high-dimensional vector representing the activity of thousands of genes. By clustering this data, scientists have been able to identify previously unknown subtypes of cancers. These different clusters, or subtypes, often respond very differently to treatment, paving the way for personalized medicine where therapies are targeted to a patient's specific cancer profile. PCA's ability to simplify complexity and fight the curse of dimensionality is equally transformative. First, image compression and facial recognition. An image is a very high-dimensional object. PCA can be used to reduce this dimensionality while preserving the essential features. In facial recognition systems, for instance, PCA can distill a complex image of a face down to a much smaller set of principal components, sometimes called eigenfaces. This not only makes storing and comparing faces much more efficient, but also helps the system focus on the features that are most important for distinguishing one person from another. In finance, the stock market is a chaotic system with thousands of individual stocks moving every second. Are these movements all independent, or are there underlying forces driving them? PCA can be applied to a massive dataset of historical stock returns to identify the main factors or principal components of market movement. These might correspond to broad economic trends like interest rate changes, industry-specific shifts, or overall market sentiment. This allows portfolio managers to better understand and manage risk. And in genomics and proteomics, as with clustering, dimensionality reduction is vital. A dataset measuring the levels of thousands of proteins in patients with Alzheimer's disease is impossible for a human to analyze directly. By applying PCA, researchers can reduce these thousands of protein dimensions down to just 2 or 3 principal components. They can then create a 2D or 3D plot of the patients. Often, this reveals clear patterns, such as patients with the disease clustering in one area of the plot and healthy individuals in another. By examining which original proteins contribute most to the principal components that separate these groups, scientists can generate new hypotheses about which proteins are most involved in the disease. We've covered a lot of ground, and it would be easy to walk away with the impression that unsupervised learning is a kind of magic box. You pour in raw, messy data, turn the crank, and out pops pure, unadulterated insight. This leads to one of the most common and dangerous misconceptions about this field, that unsupervised means no human intervention is required. Nothing could be further from the truth. While it's true that the algorithm learns without the guidance of labeled data, the entire process is orchestrated, guided, and ultimately judged by a human expert. Unsupervised learning is not an automated decision-maker. It is a powerful partnership between human intelligence and algorithmic computation. The human plays several indispensable roles. First, data preprocessing and feature engineering. Unsupervised algorithms, particularly distance-based ones like k-means, are extremely sensitive to the scale of the input data and the presence of noise. If one feature is measured in millions, like income in dollars, and another is measured on a scale of 1 to 10, like a satisfaction rating, the income feature will completely dominate the distance calculations, leading to meaningless clusters. It is the data scientist's job to intelligently clean the data, handle missing values, and scale the features appropriately so that the algorithm can produce valid results. Second, algorithm selection and parameter tuning. As we saw, there are many types of clustering algorithms. Choosing the right one for the problem at hand requires expertise. Furthermore, tuning hyperparameters, like choosing the value of k in k-means, is a critical step that relies on a combination of heuristics like the elbow method and, crucially, domain knowledge about the problem. Third, validation and interpretation. This is the most important human role of all. An unsupervised algorithm will always find patterns. K-means will always return K clusters. No matter what, the crucial question is, are these patterns meaningful, or are they just statistical artifacts? The algorithm cannot answer this question. A human expert must step in to validate the results. Do the discovered customer segments actually correspond to distinct, actionable groups of people? Do the identified gene clusters align with known biological pathways? This step of interpretation is what transforms the raw output of the algorithm into actual knowledge and insight. This reality leads to a more sophisticated understanding of what unsupervised learning truly is. It is not a replacement for human analysis. Rather, it is best understood as a powerful exploratory instrument, analogous to a telescope or a microscope for data. A telescope does not understand astronomy. It is a tool that gathers and focuses light in a way that allows a human astronomer to perceive celestial objects that were previously invisible. The astronomer points the telescope, adjusts the focus, tunes the parameters, and interprets the resulting images to derive scientific insight. Similarly, K-means does not understand customer behavior. It is a tool that organizes data in a way that allows a human marketing analyst to perceive potential customer segments that were previously hidden in the noise. The data scientist points the algorithm at the data, tunes its parameters, and interprets the resulting clusters to derive business strategy. This reframes the drawback of needing human interpretation into the core function of the paradigm. The goal is not to automate discovery, but to augment and accelerate human discovery. It is a collaborative process where the machine's ability to sift through immense complexity enhances our own innate human ability to recognize patterns and create meaning. So, we've journeyed into the world of learning without a teacher. We've seen that unsupervised learning isn't about predicting the known, but discovering the unknown. We've equipped ourselves with the tools of clustering to find groups and dimensionality reduction to simplify complexity. We've deconstructed the elegant dance of K-means and the powerful perspective shifting of PCA. We've faced the daunting curse of dimensionality and learned how to tame it. And most importantly, we've learned that unsupervised doesn't mean unminded. It is a powerful partnership between human curiosity and algorithmic exploration. This ability to find the hidden signal in the overwhelming noise of modern data is one of the most critical and creative frontiers in all of artificial intelligence. It is the foundation upon which we build understanding in a world drowning in information. We have now seen two of the three main paradigms. In our previous episodes, the algorithm had a teacher in the form of labeled data. In this episode, the algorithm had no teacher, just raw data to explore. Now we must bridge the gap between learning and doing as we dive into the third paradigm, reinforcement learning, teaching machines to make decisions and master complex tasks through trial and error.
You've been listening to AI Deconstructed, Join us next time as we unpack another layer of the technology shaping our future. Until then, stay curious. Subscribe for more.